Okay, this set of slides is the amine chapter continued, slides 10 to 14. So we'll start with another example of how amines are used in the body, typically as a drug or pharmaceutical candidate. And again, in a prodrug type fashion, but not really. This is where you can kind of see the acid-base chemistry of an amine working for us when we're looking at a molecule that requires the nitrogen to pass through maybe a cell layer. So before we get started on amine reactions, let's take a look at this other cool example. This one pertains to allergy medicines. So allergic reactions are triggered by binding of histamines to H1 receptors. Compounds that compete with histamine binding with H1 receptors without triggering the allergic response are called antihistamines. We talked a little bit about that in the previous slide for the Benadryl. For a compound to exhibit H1 antagonism, it must possess two aromatic rings in close proximity and a tertiary amine. So let's consider diphenhydramine. The amine is in equilibrium with its ionic form, and in physiological pH, the ionic form slightly predominates. So you can see that in the equilibrium arrows I drew. Remember, the amines in physiological pH slightly prefer to be protonated. So then they are ionic, okay? And we know that ionic compounds are very, 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 very polar. And again, like dissolves like, so you can adhere to all the properties of an ionic compound, as opposed to the neutral form, which is all covalent. And sure, it has some polarity to it, but the polarity difference between neutral and ionic is very different. But, so here's the key. We need to get into and across a cell membrane, right? So here's the equilibrium I just showed you, where the ionic system slightly predominates. But in order to get into the cell, it can't be ionic. The polarity of the ionic system keeps it from penetrating through the cell wall, or through the cell, I should say, through the cell membrane. And so only when it's in its neutral form does it pass through the cell. Now the problem is, right, now once it gets into the cell, so this box is representing the cell. I can do that in green. Here's the cell. Okay, so now think of Le Chatelier's principle, what happens if we've got this equilibrium outside the cell, but whenever it's in a neutral form, it will pass into the cell, thus eliminating itself from the equilibrium. What does Le Chatelier's principle do? So this second image shows that the molecule, for the most part, is now across the cell membrane, and now it's empty here. So Le Chatelier's principle resets up its equilibrium, right? So outside the cell, the equilibrium is reestablished. So more of the ionic turns into neutral. Okay, what's happening inside the cell? Well, the neutral reestablishes an equilibrium as well, right? Because it's empty. So empty outside the cell reestablishes equilibrium. More can enter the cell, and the more that enter the cell, it's empty. So a new equilibrium establishes inside the cell. And understand that it's only in this ionic state that the drug can actually bind and do its antihistamine activity. So we're relying on Le Chatelier's principle to get us across and reestablish the equilibrium once inside. Really cool chemistry. Okay, now let's talk about the chemistry of amines. This is the last chapter in Organic 2, and you'll be happy to know that we have exhausted all possible mechanisms. So what we're going to see, a lot of what we're going to see, is going to be review. Review in a way that they're reactions we've already covered, but we're looking at it from the perspective of maybe not the ketone, but maybe we turned a ketone into an amine and we didn't even realize it. We were so focused on the chemistry of the ketone that we didn't even understand that we were doing an amine reaction. So I'm bringing back a lot of old chemistry and just showing you the perspectives of from the perspective of an amine. Now, the first thing we want to do in making an amine is to figure out how to make boutique amines, right? What I mean by that is if I wanted to make a primary amine, okay, so I want, let's say this is my goal right up here. I want a primary amine, okay? So I'm trying to make this very specific starting material. To do so, the first thing that people thought to do was, well, let's just do some SN2 chemistry, right? Let's start with the simplest form of an amine, ammonia, and let's throw on the ethyl group through an SN2 reaction, right? Okay, that shouldn't be too difficult. And so we find that the nitrogen will undergo this SN2 with a primary ethyl bromide, and you'll get to your first equivalent of the ethyl ammonium species. Okay, and what they did is then they would add things like sodium bicarbonate or potassium carbonate. Oops. Let me see. What did they add typically? Oops. I think it was typically potassium carbonate. So one of those. And so this would just take off the extra proton. Oops. So we have the ethyl, and we've got our goal. Yay, right? So the carbonate can take off the extra proton, give the electrons back to the nitrogen. So this is just a little acid-base chemistry to neutralize or work it up. Okay, here's the problem. The base that they put in was not the workup. This was just to keep things moving, to take off the extra proton. But here's the problem, okay? The problem is that if I had 5 equivalents of ammonia and 5 equivalents of ethyl bromide, right? I started with an amine, ammonia. I ended with a new amine. So functionality-wise, when you're just trying to add an R group onto your amine, unlike a lot of the chemistry we've been doing, we've been changing carbonyls like ketones into alcohols. We've actually, in the process of running a reaction, changed the functional group. Here, we're not changing the functional group, we're just adding to the functional group. So the functional group you start with is actually still the same functional group you end with. It's just, in a different form. I now have a primary amine. The problem with this is that if I used up if I used up 1 equivalent, I have 4 of those molecules left, right? If I use the first ammonia reacts with the first ethyl bromide, I make 1 equivalent of the product. Here's the problem. The amine I end with is now in competition with the amine I started with. When you introduce the second ethyl bromide and you want to know starting material, the 4 starting materials, or the 1 primary amine that we just made, who's going to win as a nucleophile? The next SN2 reaction doesn't happen with your starting material so that you get 5 nice new molecules of your desired ethylamine. The problem is that whenever you add an R group, you got to remember that R groups, ethyl, methyl, etc., are electron donating groups. So I'm going to make a statement here. Oops. So the more substituted the amine, the better the nucleophile. Why? Well, I have one donating group. If I have one donating group on my nitrogen, I'm donating electron density to the nitrogen, making it a better nucleophile. So the product, ethylamine, is a better nucleophile because it has a donating group on it, making the nitrogen more electron rich, making it a better nucleophile. The base takes off the extra proton, and now I have diethylamine. I have a secondary amine. So I've used up my one product. I've used up another equivalent of my ethyl bromide. I have 3 ethyl bromides left. I have 4 ammonias and I have 1 secondary amine. Okay, so the next equivalent of ethyl bromide, if you can guess, I have a di-substituted nitrogen now. I have 2 electron donating groups on this product versus ammonia, which has none. This nitrogen, the more I keep adding carbon groups to it, the more nucleophilic the nitrogen becomes, because the more substituted, the more electron donating groups I add, right? Because our groups are electron donating by induction. So if I just keep adding donating group and another donating group and another donating group, I'm actually making the nitrogen more electron rich, which makes it a better nucleophile. So the next equivalent of ethyl bromide reacts with the product, not the starting material again. Another SN2. And now I'm here. Now I have triethylammonium. This is not getting me to, I'm way past my goal now, right? I've made my goal and then I just kept going, right? I had no control over it. It just keeps alkylating. And then the base comes in and takes off the extra proton. And now I'm at, oops, I'm making a lot of oopses today. Now I'm at triethylamine. And I still have one of these now. I still have 4 ammonias left, but I'm dwindling my resources of ethyl bromide. Guess what? It does it one more time. This is now the most nucleophilic nitrogen, and it is ready to do an SN2. So we end here. Tetraethyl ammonium bromide. So we end at this salt. That is not what I was hoping for when I set out on the goal of making this primary ethylamine. It went nuts. It's just that the product kept getting more and more nucleophilic and out-competed the starting material. And so the problem that we end up having is called over-alkylation. And as much as we want to just do a simple SN2 reaction to get whatever group we want on there in a boutique fashion, in a design fashion, we just can't operate this. So this is not a flashcard. This is showing you the problem. Now we're actually going to make lemonade out of lemons, and this problem is actually going to serve us in the future. We're actually going to use this quote unquote problem to solve a different reaction goal. But for now, I just want you to understand that you can't just simply do an SN2 and put one group on or two groups on very easily when you're designing amines. Couple more slides for you. So there are ways around this. And so the next bunch of slides are showing you how to make amines, whether it's primary or secondary, and how we can control for this over-alkylation issue. So you can kind of think of the following slides in this set of notes and the next set of slides as going over some strategies for this goal. So I'm going to keep the molecule up here as our goal. It's the same goal we had on the previous slide, and show you some workarounds. This is review chemistry in a new context. So recall that we can use nitriles, right? Nitriles are these great anions. The carbon negative is possible to have, right? The ionic carbon minus. We saw these nitriles being hydrolyzed down to their carboxylic acids in their previous chapter. But understand that they are really nice little packages that you can put different places, and they do contain a nitrogen. So if you buy this nitrile, this salt nitrile, you can do it in SN2 reaction, whereby you can put on whatever group you want. Maybe in this case, we just want an ethyl. So we've got carbon 1 and carbon 2. So we have the nitrogen. This would be carbon 1. And so we're going to add another carbon, carbon 2. So the carbon does an SN2. Notice we're not doing the SN2 with the nitrogen. We've now formed this nitrile, carbon 1, carbon 2, and this is an absolutely fine system. Remember in the previous set of slides, the nitrogen that's sp is more stable than an sp3 nitrogen, so definitively the carbon negative is the better nucleophile here, both because it's charged and nitrogens on sp, the electrons in a nitrogen that are on an sp orbital are not as reactive. So once you've put whatever group you want on and you've designed your carbon chain, all that's left now is to reduce the pi bonds away. We can do this two different ways. The easiest way that you might think is the easiest way is just to follow a SYN4 protocol. Our typical SYN4, we're just going to do this 2 times, right? Land the ship, pi bond, adds SYN4, and you end up with CH3, C, double bond nitrogen, and we have 2 hydrogens, syn, and then you can repeat the process. Hydrogen absorbs to the surface of more metal, and the SYN4 occurs. And so this is a double SYN4 reaction, reducing what essentially is a triple bond down to a double bond, down to a single bond. And now this is the same molecule as what we aimed at up at the top. We've reached our goal. You could also, once you add the R group of your choice, you could also just do a 1,2 addition with a hydride source, where the H minus, like lithium aluminum hydride, goes in and up. It quenches within the medium somehow. We talked about this before, and then you do another in and up. So it's a double 1,2 addition. Can't come back down because there's nothing, you're adding hydrogens on there irreversibly, and there's nothing to remove off of that center. And then you end up at the same place upon workup. So there you have it, two options of putting one R group onto an amine. Here's another one. We could have started with a carboxylic acid. Okay, so again, carbon 1, carbon 2. You got to design your system. Carbon 1, carbon 2. The best way to form an amide, right, which is the third one over here, is to actually go through the SOCl2, to actually change the carboxylic acid to a more reactive acid chloride. So this is just the last chapter, right? We know how to convert a carboxylic acid to an acid chloride. We then know that an acid chloride can react in a 1,2 addition in, up, down, out, and then upon workup, or the Cl probably just grabs the extra proton, and you end up with the amide. So this is all from the last chapter. We're now at carbon 1 and carbon 2. Now notice that carbon 1 is attached to the NH2. All we have to do now is get rid of the carbonyl. And if you remember the tricky reaction, this was the tricky reaction from last chapter. The one where the H- irreversibly goes in and up for the 1,2 addition. But with amides, because you only get one shot, remember it transfers and the nitrogen is more generous, kicking the OH out. And we're kind of back to where we were on that previous slide where we have this imine type system. And under these conditions, H- addition goes in and up again. And you've reduced away the carbonyl. After workup, you end up with carbon 1, carbon 2. Carbon 1 and 2 are just an ethyl group. I just drew the hydrogens in, but I don't have to draw the hydrogens in, right? Carbon 1, carbon 2. You have made your system. So you can actually, using carbonyl chemistry, very easy to purchase carboxylic acids, pretty cheap too. Go through the process of converting it to an amide and then reducing the amide down to the amine using that tricky lithium aluminum hydride in up, down, out reaction.